Good day. This is the 17th lecture of Metallurgy and Material Science. And in this lecture, we are going to discuss an important topic in MMS, that is diffusion. So, in the last class, we discussed about microstructure and we studied different characteristics of microstructure. We discussed about grains and different imperfections in the microstructure of the crystal. And from this lecture, we are going to study how can we control this microstructure, or how can we control the microstructure, thereby we can improve the strength and other properties of the material. So the microstructure is controlled by phase transformation. Okay, so this, by using phase transformation, we can control the microstructure. If you want a particular type of microstructure, we can develop that type of microstructure by phase transformation. And in that, this diffusion process has an important role. Okay, so we are actually studying, in this lecture we are studying the basics of phase transformation, and in the coming lectures we will study in detail about this phase transformation. Okay, so what is diffusion? Diffusion is a phenomenon of material transport by atomic movement. Okay, so um, what happening to the microstructure when the material is transport from one point to another point. Okay, so this is diffusion is nothing but that is a mass transfer. Okay, the mass or the atoms is transferred from one point to another point of the crystal lattice. Okay, and there are different type of diffusion, the liquid, in case of liquid or gaseous phase. We already studied the diffusion in the school days, and but here we are going to discuss about solid state diffusion. Okay, so how these atoms are moved in this crystal structure in solid phase. So that is what we discuss in this lecture. So this is the diffusion process. Here we can see. So it is a movement of solute molecule from the area of higher concentration to the area of the lower concentration. So here we can see this is a high concentration of atoms in this region, and here we can see lower concentration of atoms, this red color atom in this region. So because of this concentration gradient, what happened? This high concentration atom will move to the low concentration atom. Okay. So this high constant here, initially we have high concentration of solute atoms here, and after diffusion process we can see the high concentration solute atom move into the low concentration area, and after diffusion we got a uniform concentration of the solute atom in the entire region. So this process is called diffusion. Okay, so what is the importance of diffusion in material science? So many reactions and processes that are important in the treatment of material rely on diffusion. Okay, so for example, in this case, this is the teeth of the gear. So during the transmission of power from one gear to another gear, so we can see the power transmission is by the contact of these teeth. Okay, or by meshing of these teeth. So when they mesh each other, what happen? There will be wearing of the teeth profile. തേയ്മാനം ഉണ്ടാവും. Okay, so this wearing or wearing of the ear profile can be reduced by providing a very hard surface on the surface of this tooth. Okay, so if we can provide very hard surface on the outer area of this teeth, then we can reduce the wearing of these two ears. Okay, so if you take the one teeth, so if we can provide high hardness, we can provide very hard material for the tooth, then we can reduce the wearing of the material. Of course, hard material ആവുമ്പോൾ എന്താണ് അതിന്റെ തേയ്മാനം കുറവായിരിക്കും അല്ലേ? So if we can make this gear with a very hard material, we can reduce the wearing of the gear. But what is the disadvantage of using hard material? So if we use a hard material during the manufacturing of this gear, we need to um, provide very high-end tool, because hard material machinability is very low. Machinability of hard materials is very low. So we have to provide very high tooling or very hard tool for machining. Okay, and by using this very hard tool, the machinability, that means easiness of machining from raw material to a gear, this will be difficult, and also the cost of machinability also will increase. Okay, so that is the disadvantage of using a very hard surface or hard material for making this gear. So if you use very soft material for making this gear, then the tooth will not be hard, then there will be a wear between the wear in this tooth when they make a mesh during the power transfer. Okay, so what we can do, so instead of making the whole gear with the hard material, actually we are making only, or we are providing a hard surface. Here we can see a hard surface on the teeth profile. Okay, so instead of making the whole gear with a hard material, what we do, we make this region, that means the surface of the tooth only with the hard material. This region only made with the hard material, and the remaining regions of the teeth, is made with the soft material. So the machinability can be increased because we are dealing with the soft material while cutting the gear. And the second purpose, the wearability of the teeth also increased, or wear resistance increased because of the hard surface. We provide a hard surface on the profile of the teeth. Okay, then how can we provide a hard surface on the surface of this teeth? By carbrizing. By carbrizing method, we can provide hard surface on the surface of the teeth. Okay, so here the wear resistance only for the surface. We don't need to give entire material with the hard surface. Okay, so here I am using carbrizing process. Actually, what is carbrizing? Carbrizing is nothing but we introducing carbon. For example, this gear is made with iron. Okay, so by carbrizing process, we introducing carbon into the surface. In this area only we introducing carbon. So by introducing this carbon material in the surface become hard. Okay, the surface become hard. So by introducing carbon, the surface area will have high concentration of carbon, and the remaining area will be without less concentration of carbon. Okay, so in this area, the remaining area, the carbon concentration is low, so the region will be soft, and the machinability can be increased. And in this region, in the surface area, the carbon concentration is high, so in that area the wear resistance of the teeth also improved. Okay, so by this carbrizing process, we got a teeth with the wear resistance as well as a gear with a high missionability. So that is the advantage of carburizing process. Then how can we introduce this carbon into the surface? Okay, this is a iron material gear. So we need to introduce carbon into the surface. Okay. So here we use diffusion process. By using diffusion process, we can introduce carbon into the surface. Okay, that is the importance of diffusion process. So by this diffusion process, what is the advantage of this application? Here we got a gear with a high missionability as well as high wear resistance for this teeth. Okay, so here we use diffusion process. So this is the advantage of diffusion in case of gear. Another one is the PN junction diode. In case of PN junction diode, so this is the silicon substrate. Silicon substrate. Here we deposit some N-type material and some P-type material. Okay, and after annealing process, that is a heat treatment process. Annealing process, we got a PN junction diode. So this is the area with the P region and this area with the N region. Sorry, this region with the N region. Okay, and by this method, this here also this by annealing, the process which is occurred here is diffusion. So here also diffusion is an important process for developing diodes, PN junction diodes. Okay, so that is the importance of diffusions. And so similarly, there are number of applications of diffusions in material science. We will discuss all these applications later. So what is diffusion? Diffusion is the process by which atoms or particles move from one point of the material to the another point of the material. So the diffusion can be defined as the mass flow or the atomic movement flow, in which atoms change their position relative to the neighbor in a given phase. In a given phase means in case of solid state diffusion, the phase will be solid state under the influence of a concentration gradient. Okay, there is a need of concentration gradient for the diffusion, as well as high thermal energy is required. So these are the two important conditions required for diffusion process. What is the importance of this thermal energy? For example, initially we can say all the atoms are bonded together in the crystal. All atoms are bonded together in the crystal. Okay, and under a particular temperature, under a normal temperature, these atoms are vibrating in their lattice point. Okay, they are vibrating in their lattice point. But when we increase the temperature or by the heat transfer into the material, the temperature of the entire material will increase, and thereby these atoms will be in the higher energy state. Okay, so by the increase in temperature, the atom will be in the higher energy stage. They will vibrate with a high amplitude. Okay, and at the same time, some atom will break this bond between the adjacent atom, and they move from one position to another position. It moves from one position to another position. So by increasing the temperature, what happened? The energy associated with a particle or atom increased. So they have a tendency to break the bond and to move to another position. Okay, so they may change from their equilibrium position. So the temperature is an important factor for diffusion. Another factor is the diffusion gradient. So we need a diffusion. That means this region we can see high concentration of atom, but in this region this is a low concentration of atom region. Okay, so there is a gradient, concentration gradient in this region. Okay, so by this concentration gradient, what happened? The diffusion will occur. Okay, so the diffusion rate of diffusion will be depend upon the concentration gradient. Okay, if the concentration is very high in this region, the diffusion rate also will be high. And if the concentration difference is very small, then the diffusion rate also will be small. Okay, so here we can see this is the direction of diffusion, because here we can see high concentration of particles and here low concentration of particles. So the particles will move from this point to this point. This will be the direction of diffusion. So the molecules are more densely packed on the here in the left side, and so they tends to diffuse into the space on the right side by the diffusion process. Okay, so this is called diffusion gradient. And there are two types of diffusion, basically self diffusion and interdiffusion. So what is interdiffusion? Here we can see this is the initial position. Here a copper atoms are regularly arranged here, and a nickel atom with a gray color is regularly arranged. Okay, so here one metal, the copper metal, diffuse into another metal. Okay, that is interdiffusion. So one metal or one atom, one set of atom for a particular material is diffused into another set of atom. So that type of diffusion is called interdiffusion. So here when we compare the concentration here in this region, in this region the copper concentration is maximum 100%. It is copper up to this point. And at this point copper concentration reduced to 0. Here we can see this is the orange color is the copper concentration. So at this point the concentration of copper is reduced to 0. Then from this point to this point the copper concentration is 0. Okay, so this is the graph showing the concentration of copper. And what about nickel, the gray color? In case of nickel, so here up to this point the concentration of nickel is 100%. Here we can see total atoms are, every atoms are nickel atom. So here 100% of nickel atom, and at this point what happened, the nickel atom concentration reduced to 0. So it's reduced to 0, and from this point to this point up to this region this nickel concentration is 0. So this is the initial arrangement of atoms in this setup. Okay, so after diffusion, so there is a gradient. Here we can see in this here we have 100% copper and here we have 100% nickel. So there is a diffusion gradient. So by this diffusion gradient, what happened? The material, the copper atoms and the nickel atom starts to diffuse each other. Okay, they starts to diffuse. So after diffusion, this is the figure. So here in this we can see some of the nickel atom diffuse into the region of the copper, and some copper atom diffuse into the region of the nickel. And what happened to the concentration gradient? Here initially it was 100% up to this point, but here we can see in the middle region this concentration is reduced gradually. Okay, here the concentration suddenly reduced from 100% to 0, but here the concentration is reduced gradually from 100% to 0. And what about copper? Copper similarly it is gradually reduced from 100% to 0. Okay, so by diffusion process we got this type of movement. So this type of diffusion is called interdiffusion. Here we can see two type of metals or two type of particles, atoms. Okay, so such diffusion is called interdiffusion. And second diffusion is self diffusion. In case of self diffusion, there is only single atom. A pure metal, for a pure metal the self diffusion occur, and in pure metal here we can see this is A atom, this is B, this is C, this is D. So this is the original lattice. Okay, lattice arrangement. And here in this some of the atoms under high temperature, what happens, some of the atom breaks its bond with the neighboring atom and they move from that atomic lattice point to another point. Okay, so here we can see the C is moved from this point to this point. So okay, a movement of C from this point to this point. So C is repositioned in this point. Okay, and D is moved from this point to this point. A is moved from this point to this point. B is moved from this point to this point. So such a movement of atom inside the crystal of pure metal is called self-diffusion, where the atoms of the metal just exchange in their position. Okay, just exchange this their position. So such type of diffusion is called self-diffusion, and self-diffusion does not contribute any significant effect on the properties of the material. The main reason for that is here we can see in this the atoms are regularly arranged, and here also the atoms are regularly arranged. There is no impurity atoms, there is no imperfections, just the atoms exchange their position. Okay, but by the exchange of this position there is no change in the property, because there is no change in the characteristics of the atom by the exchange of atom. So the property changed by the self diffusion will be very small. Okay. So next we are going to discuss about the mechanism of diffusion. So how this atomic movement takes place inside the atom, inside the crystal. So that is the mechanism of diffusion. So for an atom to move from its lattice point, two conditions must be satisfied. First, there should be an empty site, because the one atom which is leaving from its lattice point has to occupy another space. So there is a need of empty site inside the crystal for a perfect diffusion. Another condition is that atom must have sufficient energy to break the bond with its neighbors and migrate to adjacent sites. That is called activation energy. And this activation energy is developed by this uh, high temperature. So by providing high temperature, what happened? The activation energy of these atoms will increase, and they try to break the bond and moving from their original lattice point to another vacancy or adjacent position. Okay, so that is the second condition. Okay, so by I am providing the high temperature, higher is the probability that the atom will have sufficient energy. So hence the diffusion rate is increased with respect to temperature. Okay, and what are the different diffusion mechanism? First one is vacancy diffusion, interstitial diffusion, substitutional diffusion, self-diffusion, and self-interstitial diffusion. These are the different types of diffusion mechanisms in atoms. So first one is vacancy diffusion. In this mechanism involves interchange of an atom from its normal site to adjacent vacant site or vacancy. When this happens, a vacancy is created on another side to which another atom can move, creating a vacancy as well. So here we can see the two set of atoms with the dark color and this orange color. So here we have a vacancy. So by if sufficient activation energy is there, then this atom will break the bond with the adjacent neighboring atom. They move from this lattice point to the next vacancy point. Okay, so by this a vacancy diffusion occurs, and again a vacancy created at this point, and the just another adjacent atom move to this vacancy. Okay, and here a vacancy is created, the adjacent atom is moving to this position. So such type of diffusion is called vacancy diffusion, but the rate of this vacancy diffusion is very low, and it may take for a complete diffusion it may take years and years. Okay, so the rate is very low for the vacancy diffusion, and the rate of diffusion depends upon the number of vacancy. If the number of imperfections in the solid is very high, vacancy imperfection is very high, then the rate of diffusion also increased, and it's depend upon the temperature. If you provide very high temperature for the material, then the rate of diffusion can be increased. And the activation energy is the energy required to break the bond and to move from its lattice point to another lattice point. So the activation energy for the exchange also is an important factor for affect the rate of diffusion. Okay, so that is the first mechanism of diffusion. The second mechanism, interstitial diffusion, and this interstitial diffusion is a very important mechanism in case of alloy material. For example, while the steel, in case of steel is the regular arrangement of iron. The regular arrangement of iron, the carbon particles entering as an impurity in the interstitial position. Okay, so this is actually an interstitial diffusion. So, for example, the previous gear application where the surface is carburized using a carbon impurity. So, the carbon particle actually enter in the interstitial sites of the parent metal. Okay, in the carburizing mechanisms to improve the hardness of the surface. So this carbon atom entering in the interstitial sites of the vacant sites or interstitial sites of the or void space inside the crystal structure. So this interstitial diffusion is an important role in the alloying of the production of alloy elements in metallurgy and material science. So the migration of atom from one interstitial position to a neighboring one is one that is empty. Okay, so that migration of atom from one interstitial side. Here we can see this is an interstitial atom. Here solute and solvent is there. So one solute atom or impurity atom which is in the interstitial position before diffusion, moving from this interstitial positions to another interstitial position which is vacant. Okay, so such movement is called interstitial diffusion. And here for alloying, here this is the parent metal, like for example iron, that is a parent metal, metal A, and this is the interstitial impurity, that is metal B. So during alloying process, what happened? These metal B atoms occupy the interstitial positions of the atom A, and we can form an interstitial alloy. Okay, so this is an this interstitial alloy. Steel is an example for interstitial alloy where carbon particle entered in this interstitial positions of iron. Okay, so by this way we can produce interstitial alloy. So this is an interstitial diffusion. So what are the different factors affecting interstitial diffusion? First one is smaller atom diffuse between the atom. Okay, so if the atomic size of this solute atom or impurity atom is very small, then the chance of diffusion also will increase. Okay, but if the size is very big, it is very difficult to move from one interstitial site to another interstitial site, thereby diffusion rate will decrease. And more rapid than that of vacancy diffusion, since there are more empty interstitial positions than that of vacancy. So for vacancy diffusion, there is a requirement of vacancy. If there is any vacancy, this vacancy diffusion may occur, but here always there will be interstitial sites. So easily this interstitial atom can occupy another interstitial site. So the rate of interstitial diffusion is higher than that of vacancy diffusion. And probability of having interstitial diffusion is more than that of the vacancy diffusion. Okay, so this is a very important mechanism for creation of interstitial alloys. Second one is substitution alloy. In case of substitution diffusion, the substitution diffusion is used to create substitution alloy. Here we can see the metal A and the metal B atom, and when we compare this, we can see the size of the metal A and the metal B almost same. But here in the interstitial alloy formation, the size difference is very large for metal A and the metal B. So this metal B can easily enter in the interstitial sites. But here the metal B cannot enter in the interstitial site, but they can replace this atoms from the metal A and they can occupy in the regular lattice points. Okay, here we can see the green metal A atom is replaced with the metal B atom. So a substitution diffusion is occurred here. Okay, so substitution diffusion is generally proceeded by a vacancy mechanism. So for the substitution, there is a need of vacancy, and after creation of vacancy, the metal B atom enter in the vacancy position. So thus the interstitial diffusion is faster than that of substitution diffusion by the vacancy mechanism. Okay, so when we compare this interstitial diffusion and the substitution diffusion, interstitial diffusion is more faster because there is no need of vacancy for this interstitial diffusion. But in case of substitution diffusion, here there is a need of vacancy. If there is this diffusion only occur if there is any vacancy position available. Okay, so that is substitution diffusion. This is also important for the formation of substitutional alloy. Okay, so later we will discuss about these two things, interstitial alloy and substitutional alloy. Both the interstitial as well as substitutional alloy is formed with the diffusion mechanism. And third one is the self-diffusion. Two or more adjacent atoms jump past each other and exchange their position. So here we can see a loop of atom exchange. So each atom reposition or exchange their position with the adjacent atom. Okay, so such type of diffusion is called self-diffusion. Here, during self-diffusion or ring mechanism or direct exchange mechanism, 3 or 4 atoms in their form a ring move spontaneously round the ring, thereby interchanging their position. So they just interchanging their position. There is no creation of vacancy or interstitial position. They just exchange their lattice positions. That is the self-diffusion, and the movement is like a ring movement or by like a triangle movement. Okay, so this is called self-diffusion and takes place between the 2, 3 or 4 atoms, and it's also called ring diffusion or Zener ring diffusion, result in the several local lattice distortion. By this movement there may be a chance for local lattice distortion and require much more energy for atoms to jump. Okay, because there is no vacancy here to jump, so they have to spend more energy to jump and reposition by self-diffusion. Another one is self-interstitial diffusion. Here we can see the atom occupy in the interstitial site forces at a regular atom to leave its site to an interstitial site. So here we can see this is not an interstitial atom. Okay, this is a regular atom, and this regular atom move from their regular lattice point and occupy in the interstitial position. So such diffusion is called self-interstitial diffusion. Okay, and this diffusion is actually a very difficult process because when we compare the size of these interstitial points and the size of the atom, it will be very difficult. There will be severe lattice distortion by occupying this atom in the interstitial position because the size of the atom is very large compared to the interstitial position. So here this the chance of self-interstitial diffusion is very less because of the size difference. Okay. So this is the different types of mechanism we discussed. First one is vacancy. The atoms from the regular lattice point change their position into a vacancy point, that is vacancy diffusion. And interstitial atom diffusion, that is here interstitial atom moving from their one interstitial position to another interstitial position, that is called interstitial diffusion. Third one is substitution diffusion. Here we can see the atoms move from one lattice point to another lattice point. Okay, here a different atom is repositioning. Okay, another atom is repositioning. And self-interstitial diffusion, just the In case of self-interstitial, they just one atom move into the interstitial position. That is self-interstitial. And self-diffusion, by a ring formation or a triangle formation, they just exchange their position. That is called self-diffusion. So all these are the different mechanisms of diffusion. And diffusion is more ionic solid occur by vacancy mechanism. In ionic crystal, we already discussed about the Schottky and the Frankel defect assist the diffusion process. Okay, so Schottky-Frankel defects assist the diffusion process in case of the ionic materials. So we already discussed these two defects in the last lectures. And next we are going to study different terms associated with the diffusion. The first term is diffusion flux. Diffusion flux is nothing but it is the amount of material or atom moving per unit area across the unit area in unit time. Okay, so number of atoms or amount of material crossing a unique cross-section area per unit time is called diffusion flux. Okay, so we can say diffusion flux is equal to 1 by A dm by dt or dn by dt. Okay, so we can represent the amount of material or atoms in terms of atoms per the diffusion flux. The unit is atoms per meter square second or kilogram per meter square seconds. Okay, so both units can be used for diffusion flux. It is nothing but it is the amount of material or atom diffuse across this unit cross-section area per unit time. That is called diffusion flux. And the diffusion flux can be measured in any direction, x, y is a direction. So here in this host atom and impurity atoms move across the unit area. And second term associated with the diffusion is the concentration gradient. So here we already discussed about the concentration difference is the necessary condition for the diffusion. And here we can see due to the difference in concentration, the atoms from the high concentration area is moved to low concentration area. So concentration is the of a diffusion element is plotted versus position. See here we can see here the Ca, the high concentration, and this is the low concentration. Okay, and this plot with respect to position. And the resulting curve is known as concentration profile. And the slope of the curve is called concentration gradient or dc by dx. This is not dc by dt, dc by dx. That is the concentration gradient. Okay, what is the concentration difference with respect to distance? This is not dt, this is dx. And we can say for 2 points, if we take 2 points A and B, Ca by Ca and delta C is equal to Ca minus Cb, and the difference between these two portions, the length difference, that is Xa minus Xb, or position difference. That is a concentration gradient. And steady state, the diffusion is maybe occur in steady state or unsteady state. In case of steady state diffusion, from one end to other implies that the concentration profile does not change with respect to time. Okay, there will be perfect concentration profile. So that is the concentration profile will not change with respect to time. So that is steady state diffusion. Okay, so here we can see in this diffusion, if you take this rectangular portion, box doesn't change with respect to time, or the diffusion flux of the left hand side and the diffusion flux of the right hand side will be same. Okay, so dc by dx, the slope of this graph will be constant, and its slope will not vary for a steady state diffusion. And in case of non-steady state diffusion, the concentration profile vary with respect to time. Another important term is diffusion density, diffusion coefficient or diffusion diffusivity. Okay, and that is nothing but it is the measure of how fast one species can diffuse into another. So the rate of diffusion can be represented using the term diffusivity. Then we can relate this diffusivity with respect to thermal conductivity or electrical conductivity. So I will explain about that later. And by for a particular diffusion process, if the diffusivity is very high, then the rate of diffusion will be very fast. Okay, so that fastness of diffusion process can be determined based on the diffusivity D value. Okay, atom will have to overcome the resistance and the barrier to their movement. They have to break their bonds and they need some amount of energy, and that energy is called activation energy. Again, this is another term. So these are the terms. I will explain all the terms when we deal with this Fick's law. And then factors affecting the diffusion process. First, the nature of the diffusion species, atomic diameter, bonding, melting point of the material. So it's dependent upon the material. Some material can easily diffuse, and another material is very difficult to diffuse, and it's dependent upon the diameter of the atoms or bonding. Is it a highly strong bond or weak bond, and the melting point of the material also. Okay, and another one is concentration. The concentration gradient is an important factor. If the concentration gradient is high, then the diffusion will be faster. Okay, second one is crystal structure is also a factor. Atomic packing factor is a factor. Atomic density along diffusion direction and distortion of crystal lattice, etc. is a factor for the diffusion. And some imperfections, for example, if there is any vacancy present in the crystal structure, then diffusion will be faster. Okay, and similarly, the imperfections leads to this is the important factor which determine the rate of diffusion. And grain size, fine grains means more grain boundary, hence more diffusion paths are available for fine grained structure. Okay, so that is also a factor for diffusion. Temperature is a big factor. By increasing the temperature at a high temperature, the rate of diffusion is very high. And impurity, presence of impurity actually slow down the diffusion process. That is another factor. So these are the different factors affecting the diffusion process. And Fick's law is actually the governing law of diffusion, and we can compare this Fick's law with the other two important theories, that is about heat flow and charge flow. So I am going to explain these three terms, and I am going to compare this. The first one is flux, then gradient, then corresponding law, then material property, and in case of charge flow, you may study this charge flow or electricity flow in your physics class. So charge flow, for the charge flow, the flux is nothing but charge flux. Okay, charge flux, that is nothing but how much amount of charge cross the unit cross section area per unit time. That is a charge flux. So the unit is nothing but coulomb per meter per second. Okay, how much amount of coulomb of charges cross a particular cross section area per unit time is called charge flux. And what is the driving force for the charge flow? That is the electric potential. The potential difference is the reason for charge flow. So the gradient is nothing but electric potential, and that is dV by dx. Okay, so the difference between the for example here between these 2 points, that is at a distance dx, here V1 is the potential, or here V2 is the potential, then the difference is V2 minus V1 is dV. So dV by dx, that is the difference in electric potential, and that potential actually that actually determine the charge flux. Okay, how much amount of charge can flow per meter square per second. Okay, and corresponding law, what is Ohm's law? Ohm's law. You already study Ohm's law. What is that? J is equal to minus sigma into dou V by dou x. Dou V by dou x. Okay, so the charge flux is equal to minus sigma into, or minus, instead of sigma I can give k. This is the commonly used letter for in this law. So J is equal to minus k into dou V by dou x. Okay, that is the charge flux is equal to minus k into dou V by dou x. And what is k? K is called electrical conductivity. And what is this unit? It is equal to ohm inverse meter inverse. That is the unit of K. So here the material property is electrical conductivity, that is the constant value of this Ohm's law, and the driving factor for this charge flux is gradient electric potential dou V by dou x. Okay, and the charge flux is the amount of charges cross unit cross section area per unit second. Okay, and similarly for charge flow, we can again we can say heat flow. What about the heat flow? Heat flow. So for example, I am taking a hot medium, here a hot medium with the temperature T1 and a cold medium with the temperature T2. A cold medium with the temperature T2. So there will be heat transfer from hot medium to cold medium. Okay, so how much amount of heat is transferred, how much energy is transferred or heat is transferred per unit cross section area per second? That is the flux. Okay, so that is the flux, that is heat flux. Heat flux, that is equal to represented with Q, and its unit is joule per meter square second. How much amount of energy or heat is transferred across the cross section area per second. And what is the gradient here? The gradient is nothing but temperature difference. If the temperature is same, there will not be any heat transfer between this point and this point if the temperature is same. But here, this is the hot medium, this is a cold medium, so there is a temperature difference between these two area. That is the reason for this heat transfer. Okay, so here the gradient is temperature difference between the 2 points. So here we can say here the temperature dx is the distance between these 2 points, and here the temperature is T1 and here the temperature is T2. Okay, so and here the temperature is T1, here it is T2, and it is separated with the dx distance. So the gradient is nothing but the temperature gradient, that is equal to temperature gradient dt by dx. Okay, and the governing law is nothing but Fourier law of heat transfer, that is equal to Q. Heat transfer Q is equal to here also we can use the letter K, minus K into dt by dx. So amount of heat transfer is equal to K is called thermal conductivity into dT by dx is the gradient. Okay, and here what is the property? The thermal conductivity. Thermal conductivity. And what is this unit? Watt per meter Kelvin. That is the unit of thermal conductivity. Okay, so here here in this for heat flow, this is the four parameters and laws and gradient, etc. And similarly, so this is for charge flow, and this equation is developed by Ohm in 1827, and this equation for heat flow, that is in the earlier days 1807, this equation is developed, or this Fourier law is developed. And next one is mass flow. Next one is for mass flow. This is our area. In case of mass flow, what is the flux? Flux is the mass flux. Mass flux. That is the amount of atoms or particles crossing unit cross-section area per unit time. So we can say the unit is kilogram per meter square second. Kilogram per meter square second. So mass flux we can represent with the J value, small j value. And what is the driving force or gradient? Gradient for mass flow. For example, here a particular region with a high concentration of atom, and here the region is with a low concentration of atom. So there will be atomic movement from high concentration to low concentration. And the distance between these two regions is equal to dx. And in this area, the concentration is equal to C1, and here the concentration is equal to C2, mass concentration. So difference in concentration is equal to dc. Okay, dc by, and with respect to dx. So dc by dx is the gradient. Okay, so that is the concentration gradient. We already discussed about concentration gradient. Concentration gradient. So in the last portion we discussed this concentration gradient. So this one is the concentration gradient, dc by dx. Okay, that is Ca minus Cv by Xa minus Xv. So this concentration gradient is the gradient of mass flow. And what is the driving law for this mass flow? And here the important law of diffusion, that is Fick's law. Fick's law. Fick's law is used. What is Fick's law? Similar to this, all the laws are similar. What is that? The flux is equal to some constant into the gradient. Okay, similarly we can write Fick's law also. Fick's law is equal to J is equal to, here also we use a constant, minus D into, what is gradient? dz by dx, dou c by dou x. Okay, so this is a Fick's law. And what is the material property here? Here electrical conductivity, here thermal conductivity. What is here for mass flow? Here in diffusivity is the material property. Diffusivity. Diffusivity, and the unit or diffusion coefficient, and unit of this is meter square per second. And it is developed in 1855. It is developed in 1855. Diffusivity. Okay, what is diffusivity? We already discussed about diffusivity. Diffusivity D, that is the intensity at which atom transfer. Okay, or diffusion coefficient can be considered to measure how fast one species can be diffused into another. Okay, that is diffusivity. So these three flows, the charge flow, heat flow, and mass flow, can be, there is a relation between these three. Okay, there is a relation between these three. In terms of flux, here we have charge flux, here heat flux, here mass flux. The gradient is dV by dx, electric potential, temperature gradient, concentration gradient. Law is Ohm's law, this is Fourier's law, this is Fick's law. Our area is Fick's law. And these three are material property. That is electrical conductivity, thermal conductivity, here for mass flow, diffusivity. Okay. So next we are going to discuss about this law, Fick's law. Fick's law. Okay, and here we can, when we compare these three laws, we can see the heat flux is equal to some material property into gradient. Okay, three laws are similar. The structure is almost similar. Okay. So this is the first law of diffusion, Fick's law. Fick's law for steady state diffusion. So according to Fick's law, what is that? J is proportional to, that is heat flux is proportional to dC by dx. Okay, and this proportionality can be removed with a constant value d. So we can write J is proportional to dC by dx and J is equal to minus d into dC by dx. And these three equations we can see a minus I. These three equations we can see a minus I. And this minus sign is nothing but, this is here, for example, in case of, so here in the Fick's law, Fick's first law, Fick's first law, we got J, the flux, mass flux is equal to, mass flux is proportional to dC by dx, or J is equal to minus d into dC by dx, minus d into dC by dx. So for example, I am taking a unit cross section area. This is a unit cross section area. In that unit cross section area, there is a concentration difference. So I am plotting a graph in this across this unit cross section area. Here, this is the concentration difference. Here I have C1 concentration, and here I have C2 concentration. Okay, and here this is X1, and here it is X2. Okay, and here what is the gradient? Gradient is equal to dC by dx is equal to C1 minus C2 divided by X1 minus X2. Okay, so we got a concentration gradient. And what is the slope of this concentration gradient? Sorry, what is the slope of this line? Slope of this line, that is nothing but this dou C by dou x. Sorry, dC by dx. Okay, and here we can see the slope is negative. It's a negative slope. Okay, so this is the decreasing direction. Okay, or the here mass transfer is in the decreasing direction. So that is why we give a negative sign here. For this, I am giving a negative sign. Okay, so here here J is positive and this dC by dx is negative. Okay, so to maintain this D as positive, to maintain this diffusivity, that is a material property, so this should be positive, this D should be positive. Okay, so and this one is negative, dou C by dou x is dC by dx is negative because of this decreasing concentration. So this is negative, and we have to maintain this diffusivity as positive. That is why we give a negative sign here. Okay, so that is minus d into dC by dx, and there is no this is just indicating the direction. Okay, here in this three equation we can see this negative sign, so that is just indicating the direction. In case of charge flow, the charge is flowing from high potential to low potential, so that direction is indicated with this negative. And here this D is called diffusivity or diffusion coefficient, and for D, B is equal to, from this we got J divided by dc by dx. And what is the unit of this? Unit of this is equal to, for J, the unit is kilogram per meter square second. That is the amount of mass flow per meter square per second. And DC, unit, that is equal to kilogram per meter cube. That is the amount of mass transfer per meter cube or volume. Okay, divided by dx is the distance, that is meter. So we got a meter square per second. That is the unit of diffusivity D. Okay. So this is the first law of Fick's. Fick's first law, that is the governing law of diffusivity. So here in this we can say this J is equal to, we already derived the J value. What is J? So J is equal to 1 by A into dm by dt, or the number of atoms crossing unit area per unit time. Okay, so number of atoms is expressed with the dm, unit area, unit time. So J can be expressed by 1 dm divided by A into dt. So similar thing we can substitute here. Instead of dm, here we use dn, number of atoms. Okay, so 1 by A into dn by dt. That is a flux, and that is equal to, from the Fick's law we got J is equal to minus d into dc by dx. So that is equal to, J is equal to minus d into dc by dx. From this we got dn by dt is equal to d into the area is towards this side, minus d into A into dc by dx. Okay. So here dn by dt is the number of atom crossing a cross-section area per unit time, and minus sign, material transfer in the downward concentration gradient, that is why we give minus sign, and A is the cross-section area, and dc is the dc by dx is the concentration gradient. Okay, so this is the equation we can derive from Fick's law. So this one is the Fick's law, J is equal to minus d into dc by dx. So this is the governing law for the diffusion. And based on this we have a problem based on the Fick's first law, and here we can see an iron plate, and this is a carburizing surface. That means we introduce some carbon particles in this area, and this is a decarburizing surface. So there will be a concentration difference between this iron plate, and if a condition of steady state is achieved, calculate the diffusion flux J. We have to calculate J value of carbon through the plate if the concentration of carbon at the position of 5 and 10 mm. So 5 and 10 mm is given. That means Xa and Xb is given, 5 and 10 mm. And beneath the carburizing surface is 1.2 and 0.8. Okay, so the concentration also given at these 2 points. So you can use this equation, J is equal to minus d into dc by dx, dc is equal to Ca minus Cb, dx is equal to Xa minus Xc. So diffusivity of the material is given, that is equal to diffusion coefficient is equal to 3 into 10 raised to minus 11 into Ca is equal to 1.2 is given, 0.8 Cb is given, divided by 5, that is Xa, 10 Xb. From this we got diffusion flux is equal to 2.5 into 10 raised to minus 9 kilogram per meter square second. So this is a problem based on Fick's law. So in the next lecture we will discuss about the second law of diffusion, that is Fick's second law. Okay, so that is about diffusion, the introduction about diffusion and Fick's first law. Thank you.